You have probably noticed something. The same AI that cost a fortune and answered slowly a year ago is now faster and cheaper, sometimes by a lot. And the obvious assumption is that they quietly swapped in a smaller, dumber model. You are getting a worse answer so they can save money. The catch has to be hiding somewhere. But here is what should genuinely surprise you. For the centerpiece trick in this episode, the answer you get back is not just similar, and it is not merely close enough. It is the exact same answer, word for word, provably identical to what the slow, expensive version would have said. They did not make the model worse. They stopped making it work so hard. So this whole episode is really one idea. How do you do less work per word without changing a single word of the answer? To see how, you have to remember the one fact from last episode. When the model writes its answer, one word at a time, the slow part is not the math. The slow part is hauling the model's billions of weights up from memory for every single word. The math units, the part that actually computes, spend most of that time just standing around, waiting for memory to deliver. Picture a giant factory where the machines are world-class, but they sit idle because the delivery trucks are slow. That idle time is the whole opportunity. So every trick in this episode is really just one move, played 5 different ways. Either you fill that idle time with useful work, or you shrink what the trucks have to carry. That is it. Hold that picture, a half-empty engine, and watch us fill it. Here is the most beautiful trick in the whole engine. Remember, once the big model's weights are loaded from memory, checking one word or checking 5 costs almost the same, because the expensive part, the loading, already happened. So you hire an intern, a tiny, fast model that races ahead and guesses, say, the next 5 words. The big expert model then verifies all 5 in one single pass, and because its weights were already up, that pass costs about as much as producing one word would have. It keeps the longest run of guesses it agrees with and discards the rest. Guesses were good. You just got 5 words for the price of 1. Guesses were bad. You fall back to 1 word and lose absolutely nothing. The intern drafts, the expert only checks. This is called speculative decoding, and on a single stream it can roughly double or triple the speed. Now the part most explainers wave their hands at, and the part that should win your trust. How can this possibly give the identical answer? If a fast little model is doing the guessing, surely it nudges the result, even a little. It does not. Through a careful method called rejection sampling, the words you keep are mathematically guaranteed to follow the exact same probabilities the big model would have produced entirely on its own, identical down to floating point rounding. It is not an approximation. It is the same distribution. Even the randomness, the temperature setting you might remember from Season 1, comes out exactly the same. So this is genuinely free speed, with one honest footnote worth keeping. The pure version, draft, verify, accept, is provably lossless. A few faster cousins relax that checking to squeeze out a little more speed, and those do trade away a sliver of exactness, so it is worth knowing which one you are running. But the headline holds. You can go several times faster and actually prove the answer never changed. And recently this got sharper. The strongest version does not even hire a separate full model. It bolts a tiny draft head onto the big model itself, one that reuses the big model's own internal features to guess ahead, so there is no second model to load. And the way people measure it tells you exactly what matters. Not some probability of being right, but how many words it gets to keep per check, what they call the acceptance length. The best of these keep something like 5 to 7 words at a time, which in practice tends to mean a few times faster, sometimes more, depending on how predictable the text is. This approach has a name you will see, Eagle, and it is now the default baked into the major serving engines. Some models go even further and bake the guessing right into their own weights, predicting their own next word and getting it right something like 8 or 9 times out of 10, for nearly twice the speed, with no separate drafter at all. The trick that started as a clever research hack has quietly become the standard way fast models run. Speculative decoding filled the idle time. The next family shrinks what the trucks must carry in the first place. Here is the whole idea. By default, every one of the model's billions of weights is a number stored in 16 bits of precision. Quantization simply stores each one in fewer bits, 8, 4, sometimes less. Picture the whole spread of weight values as a smooth hill. Quantizing snaps every value onto a coarser grid of buckets. 8 bits gives you fine buckets, and the hill barely changes shape. 4 bits gives wide buckets, and the hill starts to blur. Fewer bits means less memory and less to haul up from it, but more rounding error. That is the entire trade. Now, the names around this confuse almost everyone, so let me kill the most common mix-up in one stroke. You will see GGUF everywhere, and people talk as if GGUF shrinks the model. It does not. GGUF is just a file format, a container the shrunken weights are saved in. The methods that actually do the shrinking are separate algorithms, with names like GPTQ and AWQ. And how many bits you keep, the precision has its own names: FP8, INT8, INT4. Format, algorithm, precision, 3 different things that everyone blurs into one. So does 4 bits ruin the model? Here is where the honest answer matters, because the headlines get it wrong in both directions. Roughly, and this swings with the model and the method, so hold the numbers loosely, 8-bit floating point is nearly lossless. 8-bit integer costs you maybe 1 to 3%. And here is the surprise that catches most people. On big models, shrinking just the weights to 4 bits can rival 8-bit quality. There is even a careful research paper whose title sounds like a battle cry for full precision: "Give me 16-bit or give me death." And its actual finding is the exact opposite of what the title suggests, that most of the time you simply do not need the bigger format. What makes 4 bits work this well is a clever insight. A method like AWQ noticed that only about 1% of the weights really carry the model, the salient ones. So it protects just those before the shrink and lets all the rest drop to 4 bits with barely a scratch. And recently, 4-bit precision moved into the chips themselves. Open Tools shipped one flavor of it first. The big GPU makers added their own a little later. And the real frontier now is training in 4 bits from the very start, not just shrinking a finished model afterward. 2 more faster now, both the same move. First, sparse attention. To write each new word, the model looks back at every word that came before, everyone held in that memory from last episode. On a very long document, that backward look gets brutally expensive. But it turns out most of those glances barely matter. So newer systems let the model attend to only the most relevant past words, a top slice instead of all of them, with almost no hit to quality. One such method, shipped in late 2025, helped a major provider cut its prices by more than half. Second, and this one is almost obvious once you see it, reading your prompt and writing the answer are 2 totally different jobs. Reading the prompt is heavy on math. Writing each word is heavy on memory. They want different hardware. So the newest serving systems literally split them onto separate machines. One cluster that only reads prompts, another that only writes answers, handing the partly finished work between them. It is called disaggregation, and on the newest chips it has reported up to around 7 times more work from the same fleet. Same idea again. Stop wasting the half of the engine that is standing still. So step back and see the whole engine as one idea. It is never about a smarter model. It is about an engine that spends half its life standing still, waiting on memory, and every trick is a different way to stop the waiting. Speculative decoding fills the idle time by checking 5 words in the time it took to make one, and proves the answer never changed. Quantization and sparse attention shrink what has to travel through memory in the first place. Disaggregation gives the reading job and the writing job each the machine it actually wants. 4 different names, 1 move. Never let the engine stand still. And this matters more every day because the center of gravity has tilted. The work of running these models, answering everyone's questions, now vastly outweighs the work of training them in the first place. By one industry estimate, the demand for that running has already grown something like 1 millionfold over just the past 2 years. So the unglamorous engineering in this episode, doing less work per word without changing the word, is quietly where most of modern AI now actually lives. Next time, we open the model itself and ask how something with hundreds of billions of parts is built so that only a small slice of it ever has to run for any given word.